Welcome back to another Algebra 2 online instructional video. We have just concluded the unit on sequences and series. And now we are going to start a new unit. This unit is all about probability and statistics. So this unit is going to be a considerable amount different from most of the things that we have done up to this year. There's going to be some techniques we see that are reviewed, but it's going to be almost a fresh start for everybody. So one of the things that we're going to find with probability and statistics in this unit is we're going to be faced with a lot of word problems, reading scenarios, and situations that we have to be able to read for important information. There are some key terms that we are going to rely on, and I'm going to use some of those now or let you give you some definitions here. The first one is what we call an experiment. An experiment is a task with a well-defined set of outcomes. So, for example, let's use an instance of shooting a basketball. So let's say I shoot a free throw. And let's say I have more than just miss and make. Let's say I take my options as I make it and it's nothing but net. I make it, but I hit the rim. I make it and use the backboard, or I miss. So the experiment is the shooting of the basket. The outcomes are the result, or is a result from a single trial of an experiment. So let's say I'm a pretty good basketball player, and I shoot it, and I make it nothing but net. So the outcome then would have been the make that was nothing but net. Now, an event is a set of one or more outcomes. So an event could be making the shot with nothing but net. An event could also be making the shot in general. In that case, there are three possible outcomes that I listed. Making the shot with nothing but net, making the shot hitting a little bit of the rim, or making the shot using the backboard. A sample space, or sorry, an event is a term that we're going to see very frequently, and we're going to use a capital E to denote events. So when you see a capital E here, we're going to use that. It's referring to the set of one or more outcomes. A sample space would be a set of all possible outcomes. So the sample space then would be the four possible options that I gave you. Missing, making, hitting the backboard, making, hitting the rim, and making nothing but net. So if I include all four of those options, that is the sample space. A sample space is a term that we're going to use very frequently as well, and we will denote that one with a capital S. So let's actually take a look at some examples dealing with an experiment where there's outcomes that we can break down into events and samples in the sample space. Problem number one says, for each of the following, state the sample space and the probability of a single outcome. Then define any two events, E relative to S. So problem one, example A, says that we are rolling a single standard six-sided die. So remember, if you've seen a die before, hopefully, a dice has six sides to it, and they are numbered by the dots on the sides of the dice, 1 through 6. So the sample space, let's back that up. The experiment would be rolling the dice. The outcomes would be what number that are going to come from rolling the dice. So the sample space then would be the set of all possible options. So you could roll a 1, you could roll a 2, you could roll a 3, you could roll a 4, a 5, or a 6. And the question also asks to list the probability of a single outcome. So a single outcome would be 1 out of 6. So you have a 1 in 6 chance of rolling a 1, a 1 in 6 chance of rolling 2, a 1 in 6 chance of rolling a 3, and so on and so forth. Now an event, there could be multiple different kinds of events here. So let's say event 1, it says give any two events. So let's say event 1 is that we would roll 3. So we have a 1 in 6 chance of rolling a 3 because there's 1 3 in the sample space and there are 6 total outcomes. Let's say event 2 is rolling a 2 or a 3. Now, the probability of this event would actually change, and we'll talk about the probability of events and how they change, why they change. But this could be an event. Event 1 here is rolling a 3. It's a single outcome. Event 2 is rolling a 2 or a 3. There's 2 different possible ways to get that event, but it would still be a single outcome. Take a look at problem B. See if you can identify what the sample space might be for flipping 2 standard coins. So, if you flip 2 coins, there are potential outcomes. The first coin could be heads. The second coin could also be heads. So I'm just going to represent that with H and then H. Another outcome, you could have the first coin be heads and the second coin be tails if you flip both coins. You could also have the first coin be tails while the second coin is being tails. And you could have the first coin be tails while the second coin is heads. So there are 4 possible outcomes that you could get. And so the sample space is heads, 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 tails, 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 and tails, heads. The probability of getting any of these outcomes would be 1 out of 4. Now an event could have had a number of different events. So let's say that my event 1 is that I've flipped both coins and both end up as heads. You could have said any of these options. Event 2, let's say event 2, an example of that is I flip the coins and one is heads, then tails. So these are singular events, but they're still events that could occur. You could have any combination of possible events from the sample space to give us an event. Okay, so you don't have to have exactly the same thing, but as long as it's an outcome that exists in the sample space, it can be considered an event. Now let's start with some basic probability. And this is something you've probably already covered in a previous class. But we want to give ourselves some foundation here. Make sure we're all on the same page. So let's say we have the probability of an event E. We don't know what E is. It could be anything. It could be any defined event. But the probability of event E, let's use the notation P of E. So this is kind of like our function notation, but P is going to stand here for probability. E we already denoted as event. So this we would say, if we were to speak it, would be the probability of event E, whatever E is. Okay? The probability of event E is going to be N of E over N of S. And so N of E would be the number of elements in an event, and the probability, or sorry, N of S would be the number of elements in the sample space. So if we go back to the previous example, or one of the previous examples, let's say um, problem 1A, where we talked about rolling a single die. Event 1, if we wanted to know the probability of rolling a 3, that would be the number of 3s that are located in the sample space, which is 1, over the number of total elements in the sample space, 6. So this would be a 1 in 6 probability. Event 2 here that I denoted was roll a 2 or a 3. So there's 2 total options that could come out of this event over still the 6 in the sample space. So this would have a probability of 1 over 3. So we can see as the number of options that occur in an event change, the probability is going to increase. So let's take a look at another example. Problem number 2. Problem number 2 says a single card is drawn from a well-shuffled deck. Define S, that is the sample space, and state the probability of any single outcome. Then define E, that is the event, as a king is drawn and find P of E, or the probability of E. So the sample space is the total options. There's 52 cards in a deck. And so you could draw an ace of hearts. You could draw an ace of spades. You could draw an ace of clubs, and so on and so forth. So you could list out all 52 options, but I'm just going to write out the sample space here using that um, notation for a set is the 52 different cards. So we know there's 52 total of options in the sample space. So the probability of any single outcome, so the probability that I draw, let's say the ace of spades, is 1 out of 52, because there's one ace of spades out of the 52 total cards. Now, in this problem, it said define E as a king is drawn. So this is E, this is the event. So if we want the probability of the event, remember the probability of an event is the number of elements in the event over the number of elements in the sample space. Well, we already said there's 52 cards in the sample space. So the number of elements in the sample space is 52. The number of elements in the event is the number of kings in the deck. So there's a king in each suit: clubs, hearts, spades, and diamonds. So the number of elements in the event is 4. So there are 4 ways that we could pull a king out of these 52 cards. So the probability of this, if we simplify, would be 1 over 13, which we can go ahead and put into either a decimal or percent. So 1 over 13. I'm going to carry this out to 4 decimals. Would be approximately 0.0769, which is approximately 7.69%. So the probability of drawing a king from any one normal deck is a 1 in 13 chance, or 7.69%. Let's go ahead and take a look at another example. In problem number 3, a family of 5 has 2 girls and 3 boys named Sophie, Maria, Albert, Isaac, and Pythagoras. Their ages are 21, 19, 15, 13, and 9 respectively. One is to be randomly selected. Find the probability that a teenager is chosen. So if we want to identify what the event is first, so we need to find the probability that a teenager is chosen. So a teenager is chosen is the event. In order to find the probability, again, we need the probability of the event comes from the number of elements in the event divided by the number of elements in the sample space. So in this case, it didn't tell us that we had to define the sample space, but if we wanted to, the sample space would be these numbers: 21, 19, 15, 13, and 9. They gave us the names. They told us that we had boys and girls, but that's not really important here. What we're looking at is if it's a teenager. So the age is what is determining the sample space here. So we have 5 people that we are selecting 1 from. So our number in the sample space is 5. The number of elements in the event, then, would be the number of teenagers that are in that sample space. So 19, 15, and 13 would all be teenagers. So the number of elements in the event is 3. So 3 divided by 5 is 0.6, which is 60%. So you could represent this probability as a fraction, 3/5, as a decimal, 0.6, or as a percent. It's a 60% chance that if we chose 1 out of this family, it would be a teenager. At this point, go ahead and see if you can pause the video and do problem number 4. In this case, you have to find the probability that an even card is drawn. Hopefully you had time to complete problem number 4. So again, the probability of the event is the number of the elements in the event over the number of elements in the sample space. The event is an even card is drawn. So 9 index cards, they're numbered 1 through 9. So if I wanted to write out the sample space, again, you didn't have to, but if I wanted to write out the sample space, it would be the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we count the total numbers in the sample space, there are 9 terms in the sample space. We need to identify how many of these are even. 2, 4, 6, and 8 is even. So 4 of these 9 are even numbers. So the number of events would be 4. So we have a 4 out of 9 chance of drawing an even number, which would be 0.4 repeating, or 44.4 repeating percent. So probability, basic probability, can be found by taking the number of elements in an event divided by the number of elements in a sample space. Now, we can continue off of this to develop some properties of probability. So there are going to be two main properties that we focus on, each having some subsections. So let's say property number 1. Let's say that we're given any sample space, and in these, so far we're under the assumption that every outcome has the same likeliness of occurring, and so we've seen that so far up to this case, and we're going to continue that. So given any sample space where any single event has the same likelihood of occurring, the probability of the entire sample space is 1. So this kind of makes sense. If we think about the last example, if I have numbers 1 through 9, what's the probability that I draw a number 1 through 9? Well, it's 100%. It has to be. We're going to draw a number 1 through 9 if the numbers there are 1 through 9. The probability, and here's some new notation, of not being in the sample space is 0. So this means not included in S. That kind of makes sense. So back to the last example, last problem, number 4. If I have numbers 1 through 9, and they're index cards, what's the probability that I draw a 10? Well, it's 0 because there is no 10 in that deck. So the probability that something occurs that is not in the sample space will always be 0. And the final thing to note is that the probability of any event has to be between or equal to those two values. So the lowest that we could possibly go is 0. The highest that we could possibly go is 1. And that makes sense if you think about percentages. You have percentages anywhere from 0 to 100%. There's no negatives. There's nothing greater than 100%. Now we can branch off of this a little bit as well. So let's continue to go under the assumption that we're given a sample space. I'm going to number this a little bit differently. So there's going to be 5 properties given a sample space in an event. So the probability of that event, say this is the 4th property, the probability of any event is going to be equal to 1 minus the probability that event does not occur. So this is a different way to look at probability or figuring out probability. Sometimes it gives us some shortcuts. So for example, let's say the probability, let's go with the dice. The probability that I roll a 3. Well, there's 1 3 out of the 6 total numbers. So the probability of the event would be 1/6. That's going to be the same as the probability of not the event, which is 1 minus probability of not included in the event. So what if we think about this example, what would not be included in the 3? All the other numbers, 1, 2, 4, 5, and 6. And so there's a 5 of 6 chance. So if we simplify this expression, they would be the same. Another thing to note is that we can kind of rewrite this. So the probability that event occurs and the probability that the event does not occur is always going to be 100%. And these may seem kind of generic, or they may seem like common sense, and they kind of are, but it gives us some properties that we can use to interpret situations differently that may create shortcuts in a solving process for probabilities. So let's take a look at some examples where these properties may be useful. So problem number 5 says a game is played using a spinner cut into 8 equal sections and numbered 1 through 8. Determine the probability of the following outcomes. Event 1, that a 9 is spun. Event 2, that an integer greater than 0 and less than 9 is spun. Well, if you think about this spinner, and I can draw a diagram here. It's going to be a pretty poor diagram, but you'll get the idea. 1, 2, 3, 4, 5, 6, 7, 8. We're going to spin it, it's going to land somewhere in there. So the probability of event 1 is that a 9 is spun. Well, if I look at that spinner, there's no 9 on there. So this event does not land in the sample space. So there's 0% chance that we're going to spin a 9. Probability of event 2 is that an integer, so a whole number, greater than 0 and less than 9 is spun. Well, if I look at the sample space, 1, 2, 3, 4, 5, 6, 7, 8, that's all of those numbers. So the probability of event 2 is going to be 1. So in such cases, we wouldn't have to go through the process of using this idea of the number of elements over the number of the sample space. In the first event, it's not part of the sample space, so it's 0. In the second event, it's the entire sample space, so it's 1. We can also use problems, properties 4 and 5 here in a way that's going to help us shorten work. So if we take a look at problem number 6, it says that a single card is drawn from a well-shuffled deck. What is the probability that is not a diamond? So the event here is not a diamond. Well, what we could do is we could figure out how many cards are in the deck. Or what we need to do is figure out how many cards are in the deck as our sample space. That's going to be useful. But instead of figuring out how many cards of those are not diamonds, what we could do is rewrite this equation as 1 minus that it is not E, or 1 minus the probability that it is a diamond. So in a deck, there are 52 cards. So the probability that it is a diamond is something out of 52. And there are 13 diamonds. So there's ace through 10, and then jack, king, queen. So there are 13 total diamonds there. So the probability that it is not a diamond would be 1 minus 13 over 52. And we can do that in the calculator. So if I do clear this out here, 1 minus 13 over 52, that's going to give me a decimal. That decimal, so if I did that as a fraction, I wanted to list that as a fraction, that would end up simplifying to 3/4, which is 0.75 or 75%. Okay, so this is not the only way that you could do this problem, but this is how you could use one of the instances that we're looking at. What is the event? Now let me take the opposite of that event and subtract it from 1. Like problem B. We could solve problem B doing the same thing. It says a single letter is picked at random from the letters in the word divisibility. What is the probability that it is not I? So what I could do is I could find out the number of letters in there that are not I. Or I could find out the number of letters in there that are I and subtract that probability from 1. So if I read through the word divisibility and count up the total number of letters there, the probability for getting an I would be 1, 2, 3, 4, 5 out of the total 12 letters. So the probability that is not an I would be 1 minus the probability that it is I. And you can simplify this to get 7 over 12. So the probability that I get a letter other than I would be a 7 out of 12 chance. So if I wanted to put that as a decimal, that would be approximately 0.5833, or 3 repeating, which is 58.3 repeating percent. Now again, this isn't the only way that you could do this problem. You could do the probability that it is not an I, so count up the D, the V, the S, the B, the L, the T, and the Y, and take that out of the total number of 12. You get the same answer. This is just giving us options. See if you can go ahead and pause the video and complete 7 in any way that you choose. Hopefully you finished problem number 7. So problem number 7 says one card is drawn from a standard deck, so we're taking one out of the deck. What is the probability that it is not a club? So not a club is going to be our event. So what you could have done is done the probability that it is not a club, which would be out of 52. There are a total of 39 cards in the deck that are not clubs. So you could have figured out this probability that there are 39 cards that are not clubs and taken that out of 52. You could have also written this as the probability 1 minus that it is a club. So 1 minus the 13 clubs out of 52, which would still give you 39 over 52. So either way that you think about it is okay. The ratio then would come down to 3/4, which is 0.75 or 75%. So you have a 75% chance of pulling a card that is not a club. Now let's take a look at problem number 8. Problem number 8 is definitely one that's going to be easier if we use the idea of 1 minus the event does not occur. So problem number 8 says Inter-Island Waterways has just opened a hydrofoil service between two islands. The hydrofoil uses two different engines. The probability of engine type 1 failing is 0.05. The probability of engine type 2 failing is 0.03. And the probability for both types failing is 0.012. What is the probability that the hydrofoil completes the trip? So it's asking us, what's the chance that this hydrofoil is going to make the trip between the waterways? Well, we could take a look at this as, what's the chance that the probability, or what is the probability that the hydrofoil does not make the trip? So what I'm going to do, instead of trying to find the probability that it does make the trip, I'm going to subtract the probability that it does not make the trip from 1. The reason I'm going to do this is because this tells us about engine failures. So if engine 1 fails, we can still probably go. If engine 2 fails, we can still probably go. But if engine 1 and engine 2 both fail, we're not going anywhere. So the probability that we do not make the trip would be the probability that both engines fail at the same time. So if we want to make the trip, it would be 1 minus 0.012. So we can bring that down into another decimal, which is 0.988. So we have a 98.8% chance of being able to complete the trip. So here, because of the information that they give us is in relation to us not making the trip, we can change this from the probability of it happening to 1 minus the probability that it does not happen. Now, that's also going to be helpful in problem number 9. Go ahead and see if you can pause the video and figure out an answer to problem 9. Okay, well, hopefully you got an answer here. Now, this question says, two standard 6-sided die are rolled. What is the probability that the sum of both dice being greater than or equal to 5? So our event in this case is the sum is greater than or equal to 5. So if we want to find the probability of the event, we need to find the probability, or sorry, we need to find the number in the sample space and then the probability that this event occurs. This could be one way to look at it. Well, if you think about a dice, there are, if I take dice number 1, let's say dice 1, I could roll a 1, 2, 3, 4, 5, and 6. If I take dice 2, When I roll a 1 on the first dice, I could roll a 1, 2, 3, 4, 5, or 6 on the second dice. This gives me 6 different options that occur when I roll a 1 on the first dice. I could do the same thing. So I could have 6 different options that occur when I roll a 2 on the first dice. And so far and so forth all the way through 6. So there are going to be 36 total options that I could get in these dice. Okay? 6 different options on the first one, 6 different options on the second one. A quick way to find that number is doing 6 times 6. Now, so that's the number in the sample space, the 36 options that we could have. Now, the sum is greater than or equal to 5. There are a lot of options that you could get that are greater than or equal to 5. You could roll a 3 and a 3, a 3 and a 4, a 3 and a 5, a 3 and a 6. You could roll a 4 and then a 3, a 4 and a 4, a 4 and a 5, a 4 and a 6. So finding out the total number of ways to get a sum that is greater than or equal to 5 would be a little bit of tedious. What we can do instead is find the ways that we would get a sum that is not greater than or equal to 5. Or find the number of ways that we could get a sum that is less than 5. Well, I could roll a 1 and then a 1. This would give me a sum of 2. That works. I could roll a 1 and then a 2. This would give me a sum of 3. That works. I could roll a 2 and then a 1. So same numbers but different order. This would give me a 3. That works. I could roll a 2 and then a 2. This would give me a sum of 4. That works. I could roll a 3 and then roll a 1. That would give me a sum of 4. I could roll a 1 and then a 3. Again, same numbers but different order. And then I could roll, oh, sorry, sum is less than 5. So these are the total number of ways you can get numbers less than 5. So how many ways can I get a sum of less than 5? 6. So if I want to find the probability that I'd get a sum of greater than or equal to 5, it would be 1 minus the probability that I get a sum less than 5. So 1 minus 6 out of the total 36 options. So I can do 1 minus 6 out of 36, or 1 minus 1 over 6, which would be 5/6. And then if I want to put this into my calculator, 5/6 would give me a decimal of 0.83 repeating, which would then be 83.3 repeating percent. So if I roll 2 dice, there's an 83.3 repeating percent chance that the sum of those 2 dice is going to be 5 or more. So this is one that it would allow us a shortcut taking the opposite of the event, because it's way easier to count the total number that would sum to 5, less than 5, than it would be to more than 5. So this is all of these examples up to this point looked at limited numbers, or a small number of possibilities. 36 possibilities for rolling the dice, 52 possibilities in a standard deck. And believe it or not, those are small possibilities. Possibilities can become much larger. And so we're going to go ahead and develop some background information that's going to help us to determine greater probabilities. So one of the things that you see often in statistics is what we call combinations. So combinations are when you have different possible ways of coming up with um, events in a given sample space. So there's a formula that we can use to come up with the number of combinations. So let me go ahead and write this out. The number of combinations of n objects taken R at a time. So let's go to the example of a deck. In all of our problems with the example of a deck, we were saying one card is drawn. So what's the probability that one card is not a club out of the 52 cards? But what happens if we start to draw more than one card? We draw 2 cards, or 3 cards, or 4 cards. Now our probability statistics start to change as we go through. And this is where combinations come in handy. Now, the way we represent this is a subscript N, a C, and then a subscript R. You often will hear this referred to in choose R. So there's n number of our objects in a group, and we are choosing r number of objects. For the example with the deck, if I had 53 cards and I was going to draw 3 of them, n is 52, r is 3. And this changes combinations. So if I draw 1 card, there's only 52 possible options that I could have. But if I draw 3 cards, that number grows dramatically because I could have 52 different cards in the first one, then 51 different cards in the second one, and then 53 different cards in the third one. And then that order can switch around. So this is what we call a combination. What we can do is we can find this using an algebraic formula. And that algebraic formula is taking n factorial, the number of objects, over r factorial, the number of objects that we are drawing, times n minus 1 factorial. So let's take a look at just some algebraic expressions. 10a, we have a combination where there's 7, or we want to figure out how many combinations are there if there are 7 elements, and we're going to choose 4 out of those 7. So for example, if I had 7 of you guys in a class and I'm going to draw 4 guys to work on some activity, how many combinations could I draw? So how we find that is algebraically is taking n7 factorial over r 4 factorial times, sorry, I have a typo up here. This should not be n minus 1. This should be the formula n minus r down here in parentheses. So if I'm trying to find the number of combinations that I could have if I take a group of 7 and I'm drawing 4, that's 7 factorial over 4 factorial, n and r, and then n minus r. So 7 minus 4, which is 3 factorial. And we talked about how to do factorials in your calculator. So you could do this by hand, but let's not. Let's just go ahead and do this in the calculator. So factorials before in the sequence and series unit. So 7, I hit math, I go over to probability, I take the 4th option, then divided by 4, hit math, go over to probability, take the 4th option, times 3 factorial, and let my calculator do the work. So there are 35 combinations here. So if you have a group of 7 and you choose 4, there's 35 combinations. Same thing for B. So again, this is, we have a group of 8 and we're going to choose 3. So let's say the Oregon Ducks uniform is a common example. Let's say they have 8 choices of helmets, pants, jerseys, socks, etc. They have way more than that. But let's say they have 8 choices, and they're going to put 1 helmet, 1 jersey, 1 pant together, and how many combinations could they have? So that's what this 8 choose 3 would represent. So it would be 8 factorial over 3 factorial times 8 minus 3, which is 5 factorial. And then again, we could do that in the calculator. So 8 factorial divided by 3 factorial times 5 factorial. So make sure you put the denominator here in parentheses so that it is dividing by both of those. And there would be 56 different combinations they could have with those jerseys and socks and pants. Let's see if you can do C. 5, choose 2. Or a group of 5 where we're taking 2 objects. Hopefully you've got an answer for C. So this one would be n factorial, 5 factorial, over r factorial, so 2 factorial, times n minus r, which is 3 factorial. And if we do that in the calculator, 5 factorial divided by 2 factorial times 3 factorial, and that gives us a total of 10 combinations. Now, it's a little tedious to type this into your calculator. If you have a graphing calculator, you can do this much quicker. So this is the formula that we'd use. I'm not going to make you guys really do much with this formula because we have the graphing calculators that can come up with this number for us. So if I want to do 7 choose 4, essentially there's 7 items and I want to take 4 of those items. How many combinations could I have where, again, order doesn't matter, um, or order does give you a different combination. So I would hit 7, then hit that math key, go over to probability again like before, but now I'm going to come down to the third option where it says NCR. This is the combination button. So I want to put in the 7 first to represent the end. Then I'm going to select this option here. And then I'm going to put in the 4, the R, and it gives me the 35. So you don't have to worry about doing the factorials. The calculator does it for you. So taking a look at B, I would first put in 8, and I'd hit math, go over to probability, that third option, and choose R, and then put in my R3, and there I have it, 56. One more time, C, I would type in the 5, the N first, go math, probability, number 3, 2 for R, and it gives me 10. So the calculator can find, we have this formula, but what we're going to do is use the calculator henceforth moving forward. Let's go ahead and take a look at problem number 11. So this is going to come into play in problem number 11. So now we're going back to a deck of cards, but this time we're drawing 5 cards. 5 cards are drawn from a shuffled 52 card deck. Calculate the probability of event 1, all 5 cards are face cards, and event 2, all 5 cards are hearts. So let's start with calculating the probability for event 1. So the probability for event 1 is, again, the number of elements in event 1 over the number of elements in the sample space. Oops. So because we're dealing with a combination here, to come up with the number of elements in the event and the number of elements in the sample space, we have to look with that combination formula. So let's start with event. How many possible options do we have in event 1? Well, it says all 5 cards are face cards. So how many face cards are there? There's a jack, there's a queen, and there's a king of each suit, and there's 4 suits. So there's a total of 12 face cards. So we wanted the probability that all of the cards are face cards. So what we want is, out of those 12, we want to choose 5 of those. That's going to be the number of possible ways that you can come up with 5 face cards, drawing 5 cards from a deck. So the number of elements in the event, just the event, is 12, choose 5. Now we have to do something similar for the sample space. We're still going to choose 5 cards out of the sample space or out of the deck. But in this case, we have 52 cards that we are drawing from. So the denominator of this, again, is the sample space. So this is all 52 cards. We're going to draw 5 out of those 52. So the total number of combinations there is the total of elements in my sample space. The numerator is 12, choose 5, because we have 12 total face cards in that deck, and we want to get 5 of those. So the number of combinations there is the number of elements in the event. So in order to find this, we would have to do, in our calculator, we can use the probability button, or the combination button here. So I'd type in 12, then hit the math key, go over to probability, choose the third option, and then 5. So 792. There are 792 combinations where you would come up with 5 face cards. And again, they can be drawn in different orders to give you different combinations. Now, how many combinations of cards could you get all together? That would be 52. And then go to math, probability, and choose R, choose 5. There are 2,598,960 different orders of cards that you could draw if you're drawing 5 cards out of a deck. So this gives us the probability that all of the cards are going to be face cards, all 5 of them. So what we would do is take 792 divided by that number, 2,598,960. And this would give us our decimal. So remember, if you get this in the calculator, this is times 10 to the negative 4. So we'd move the decimal place over 4 spots to get a decimal. So this would be 0.0003 approximately, which if we put into percentage would be approximately 0.03%. So very small number here. The probability that we are going to end up with all 5 cards being face cards is 0.03%. Let's take a look at another example there. In event 2, now we're looking at all 5 cards are hearts. Remember, there are 13 total hearts, ace through 10, then jack, queen, king. So the probability for event 2 is going to be similar. It's the number, again, the number of elements in the event over the number of elements in the sample space. The sample space is not changing. We're taking out of the 52 cards, we're choosing 5 of them. Okay, so our combinations, our total combinations that we could get out of the deck is still going to be 2,598,960. But the total of combinations that we could have with hearts is going to change. So now we have 13 cards that we could potentially draw from to get all of them as hearts. So we want 13, choose 5 in the numerator. We're using that number 13 again because we want them all to be hearts. So 13 choose 5 is our numerator, or the number of elements in the event. So if I type that into my calculator, using the NCR button here, that would be 1287. So I can take 1287 divided by 2,598,960. I should make sure I type that in, 2598960. There we go. And this gives me the decimal approximation. So if I'm going to round this, that decimal place would move over 4 decimals. So 0.000, this would be 49, so round it up to 5. So approximately 0.005% chance, or sorry, 0.05% chance. So the chance is greater that we're going to draw all hearts, but not by a whole lot. Okay, so when we are taking multiples out of a sample space, it's going to change. We have combinations, or we're taking multiples out of a group. We're going to have to use combinations to come up with the number of elements, and in the event, in the number of elements in the sample space. Let's take a look at problem 12. So problem 12 is a little bit more complicated. It says out of the 42 seniors at Jacoby High School, 23 are female and 19 are male. A group of 5 students is to be selected at random to attend a conference. What is the probability that the group will have exactly 3 females? So here's our event. Exactly 3 females. So this is something to key into. The word exactly is going to be very important here. Reading for information is going to be key in this target. So the probability that this occurs, again, is going to be the number of elements in the event over the number of elements in the sample space. So we're going to have combinations here because, again, we're choosing more. We're choosing 5 total students. So right here it says we're choosing 5 students. And we're choosing 5 students out of the entire group of seniors at Jacoby High School, the 42. So for the sample space is not a restriction. We're just going to take 5 out of 42. So 42, and we're choosing 5. Now, the numerator is going to create a different type of situation than what we've seen to this point. We want exactly 3 females. So let's focus on females. There are 23. So we are going to choose 23 female. Out of the 23 females, we want 3 females. So 23, choose 3. But this is not the end, because in the numerator, remember that we are choosing 5 total students. In the numerator, we're only accounting for choosing 3 so far. So if I'm going to choose, out of 42 students, if I'm going to choose 3 that are female, I must also have 2 that are male. So I'm going to have, out of the 19 males, I need to choose 2. When we have events like this, where we're going to create multiple combinations in a single event, we have to multiply those values together. So we want to multiply the combinations that we could have of choosing female times the combinations that we could have of choosing males. And that's going to give us the number of combinations in the event. So you can do this in the calculator. 23 choose 3 times 19 choose 2. I'm putting this in parentheses to make sure it's taking these expressions and then multiplying them together. And this would be 302,841. So if I choose 3 females there are 302,840 ways, 841 ways I could do that. Now, out of the total students would be 42, choose 5. There are, in general, 850,688 different combinations of students that I could have. And this is accounting for like having all females and having all males or numbers that are disproportionate. And again, order can vary through here and give you different numbers or different combinations. So we want to divide these two numbers. So 302, 841 divided by 850, 668. And this would give us roughly 0.3560, or approximately 0.3560. So we have a 35.6% chance of drawing 3 females, exactly 3 females, which would be 3 females and then 2 males. So if we have different options that come together in our event, we do have to multiply those together. Now, we do have some additional topics to consider here with probability. These were all what we would call exclusive events, but we have probability that's going to occur in non-exclusive events. So this would be when different events may share the same outcome. So for example, let's say I choose out of any given class, let's say any Algebra 2 class, I want to find the probability that I select, I don't know, 1 student, and that student is either a sophomore or a junior. Pretty high probability, but these would be non-exclusive events because it's what we call basically an or situation. You could be one or the other. So we have a formula that we're going to apply for this. So the probability of the 2 events. Event 1 in that case would be sophomore. Event 2 in that case would be junior. So if I want to find the probability that it's a sophomore or it's a junior, and we've seen this symbol before. Remember, that symbol is basically the word or. I can find this by taking the probability that it is a event 1, a sophomore, adding that to the probability that it is event 2, a junior, and subtracting that it's the probability of event 1 and event 2. We've seen that symbol before. Again, that symbol means basically and. So this is a bad scenario, I guess, but the probability that I would choose a sophomore or a junior would be the probability that it's a sophomore plus the probability that it's a junior minus the probability that it is a sophomore and a junior. So let's look at a problem that has a little bit more application to it. Problem 13, it says, what is the probability that a club or a face card is drawn from a standard deck of 52 well-shuffled cards? So in this example, basically event 1 is that we're going to draw a club. Event 2 is that it's going to be a face card. The reason that we call these non-exclusive events is because there are some cards that are both clubs and face cards. So this is when we have to use this formula. If there were no cards that were clubs and face cards both, these are what we call exclusive events, and we would not use this formula, which is kind of the example I gave before. But when you have overlapping events where they can be both a club and a face card, then we have to use this formula. So the probability that it is a club or the probability that it is a face card is the probability that we have a club plus the probability that we have a face card minus the probability that we have a club and a face card. So we're drawing one card. This makes this a little bit more simple here. So going back to our counting techniques, there are in a deck 52 cards, and 13 of those are clubs. Again, ace through 10, king, queen, jack. So the probability that we get a club is, or the probability of event 1 is 13 out of 52. The probability that we get a face card, or the probability of event 2, then would be how many face cards are there in the deck? Well, there's jack, king, and queen. There's 4 suits, so 12 out of 52. Now, we do have to subtract the probability that this is a face card and a club. So how many face cards are clubs? Well, there's a jack of clubs, a king of clubs, and a queen of clubs. There are 3 that are both of these. So to find the true probability that we're going to have a club or a face card, we want to take the probability of the first event plus the probability of the second event minus the probability that it's both of these two things. And so if I simplify this, this would be 13 plus 12, which is 25, minus 3, 22 over 52. You could simplify that fraction if you wanted to give your probability as a ratio, but let's go ahead and do decimals and percents. That's more common. So this would be approximately 0.4231, or approximately 42.31% chance that if we draw a card, it is going to be either a face card or it is going to be a club. So again, we're using this formula when events have overlapping occurrences. We could have a face card and a club in this example. Let's take a look at problem number 14. Problem number 14 says the personnel department of a company has compiled data on the numbers of employees who have been with the company for various periods of time. The results are shown in the table below. If an employee is chosen at random, what is the probability that the employee has 4 or few years of service? What is the probability that the employee has 9 or fewer years of service? So let's start with 4 or fewer. And let's make this event 1. So 4 fewer years of service is event 1. And so that works because event 1 is shown in our table. So if I want to find the probability of event 1, again, that is the probability of the number of elements in the event, which we can see from the table is 157, over the number of elements in the sample space. So we need also the total number of employees that work for the company. So we can find this by adding each one of these. So there's no overlap. They're either 0 to 4, 5 to 9, 10 to 14, or so on and so forth. So we can add these numbers together. 157 plus 89 plus 74 plus 63 plus 42 plus 38 plus 37 plus 21 plus 8. Hopefully I added those all together correctly. There are 529 employees. So the probability for event 1 that there are 4 or fewer years of service is 157 out of 529. This one is a pretty straightaway little counting technique we can use here. So 157 divided by 529 is equal to 0.2968 approximately. So approximately, I'll write my answer down here below, approximately 29.68% have less than or equal to 4 years of service. Now, The second thing that it asked us for was the probability that an employee has 9 or fewer years of service. If I look at the table, there's no set category that represents 9 or few years of service. But what I can do is I can take event 2 and make that from 5 to 9. So then the probability that we're looking for here is event 1 and event 2. Oops, not probability of event 1. This is the probability of event 1 and event 2. There we go. So this is different from what we just did before. This was an or statement where these are non-exclusive events. Let me go back. I made a mistake here. This should be an or. We want the probability that they're either in the first quarter category 0 through 4 or the probability that they're in the second category 5 through 9. But this is not what we just did. This is non-exclusive events, meaning there's some overlap in the outcomes. So for example 13, there were some clubs that were face cards. Event 1 and event 2, there were some that were both. If I look at this example, the statement here is the same. It's an or statement, but there are no values from event 1 that are also in event 2. So what I don't have to worry about doing here in this case is subtracting the and part because there is no and. So this is just the probability of event 1 plus the probability of event 2. In this case, if you tried to subtract the and part, you would have 0 numbers in the element or the event because there are 0 numbers that are both in 1 and 2. And so you don't need to subtract anything. If you did, you'd just be subtracting by 0. So if I want the probability for 9 or fewer years of service, I need the probability that they're either between 0 and 4 or 5 and 9. 0 and 4 we already did is 157 over 529. 9 and 4, between 5 and 9 then would be the 89 employees out of 529. And so if we total this out, this would be 246 employees out of 529. So these are exclusive events. Nobody falls within both the categories events 1 and events 2, so I don't need to worry about subtracting anything there. So now, what I can do is I can divide this number, 246 divided by 529, and there is my percentage, which I could put down in a decimal or a percent. So my decimal representation here would be approximately 0.4650. So approximately 46.50% have less than or equal to 9 years of service. And here would be my two answers. Okay. This is the conclusion of PS1, our introduction to probability. So as you'll notice, every single problem in here, other than our combination examples, were word problems. So we are going to have to do a fair amount of reading and reading for information. At this point, we are finished with the notes. You guys should be moving forward here to work on PS1 homework. For my honors guys, that's listed to you or listed for you on Google Classroom. For my school level guys, that is I listed for you on Google Classroom as well, but it is IXL links. Make sure that you guys are working on this homework after taking these notes and compiling questions for our Zoom meeting. Our Zoom meeting will be next week. That information will be posted on Google Classroom. If you run into any questions between now and then, feel free to shoot me an email. Thank you guys for tuning in. I hope you are staying healthy and have a great day.